last time we finished up the change of coordinates and stuff, right? Which was sort of maybe the high point in difficulty for sort of like the local maximum in terms of difficult vectors. Today we're going to do something much simpler. Section 3.6. It's called row space, column space. Row space and column space. The main result here is called the rank theorem. The rank theorem. Okay. So we start off with some very simple definitions. I guess, I don't know if they're simple, but they're sort of intuitive. At least the naming is intuitive. So these things called row space and column space. We call the span, you start off with a matrix, and you look at the span of the columns. Right, there are n columns. Right, you take your matrix, you take the columns, and look at the span. That gives you a subspace, and we call that subspace the column space of A. Okay, so the subspace that you get by taking the span of the columns is called the column space of A. The subspace that you get, right, so this is a subspace of Rm, right? If you take the rows and look at their span, that's going to be a subspace of Rn. We call that thing the row space. Row space of A. Okay, and we call the dimension of the row space of A, we call this the rank of A. The rank of A. Okay, so pretty simple ideas compared to the ideas we've had before, right? You take the rows, you take the columns, you look at their span, that's the column space. You take the rows, take their span, that's the row space. The dimension of the row space is called the rank. Yeah, Mariah.
Does column space have a rank?
Does column space have a rank?
Yeah.
We don't care about the dimension of the column space, and you'll see why later on. The reason is that it's the same thing. The dimension of the column space turns out to be the dimension of the row space. Okay, you'll see. Okay, so let's just one remark about the row space. If A and B are row equivalent to each other, then what am I going to say? If A and B are row equivalent to each other, then what can I say about their row spaces? They're the same. Right? They're going to be the same because you've just done elementary row operations to it. You're not changing the span if you change the order, or you multiply one by a number, or you add a multiple of one to the other. Right? That doesn't change the span, right? So then they have this. So if A is row equivalent to B, then A and B have identical row spaces. Right? In particular, A and its reduced row echelon form have the same row spaces. Right. So if I take a matrix and I reduce it down to its reduced row echelon form, then that has the same row space as the original matrix. What's good about reducing to the reduced row echelon form? What would be good about that? I say, I got my matrix. I start off with some matrix, negative 3, 1, 3, 4, 1, 1, 2, negative 1, negative 2, negative 3, 8, 4, 2. I do row reduction on it. I get all the way down to its reduced row echelon form, which is 1, 0, 0, negative 10, 7, 0, 1, 0, negative 2 sevenths, 0, 0, 1, 0. That's good. Well, what good did that do me? That actually did something good for me. So these guys have the same row spaces, right? Now, what do you see about these three vectors here? So the span of these three vectors is the same as the span of these three vectors, right? But for these guys, I can see very clearly that they're linearly independent of each other, right? They're linearly independent vectors, and so I know that this is a basis for the row space of this. But the row space is the same, so this is a basis for the row space here. So when you do the Gauss-Jordan reduction, you can get a basis for your row space, right? And it could well have happened that I lost a vector on the way, right? I could have gotten zeros in the last column here, right? Maybe there's some dependence between these guys, right? In that case, I would have seen that the row space is two-dimensional, right? So one can get a basis. So one can get a basis for the row space of A by Gauss-Jordan reduction. Right, or Gaussian elimination, doesn't matter. Okay, whichever one. And what you see is that the dimension, the rank, right? The rank of A is going to equal the number of pivots in the reduced form, in the row echelon form. Yeah, Martin.
Wait, so can your row space be linearly independent, but like not your column space? Is that
Say it one more time?
like, so
Yeah.
you can tell that the row space, the vectors that make the row spaces are linearly independent.
Yeah.
But so then can the column?
So look at the column. Yeah, just for the heck of it, let's look at the columns. Right? We see that these rows are linearly independent.
Yeah.
But what about the columns? Are the columns linearly independent? Well, these guys are. Right? The first three guys are certainly linearly independent. What about if we throw in the last guy? Are those four vectors linearly independent? No, right? This last guy is 10 sevenths of this guy plus 2 sevenths. Okay, negative 10 sevenths of this guy minus 2 sevenths of that guy. Right? So this is, right, there's a dependence between these columns here. Okay. And you're almost doing the proof that the dimension of the column space and the row space are the same. But I'm just going to hold on and pretend you're not that close to it. Okay. 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 Yeah, Ethan.
So how does the rank A equal the number of pivots, and like how does it compare to the definition you wrote right behind you? I'm sorry.
Yeah.
I'm not sure how it's called.
Okay, so what's the rank? The rank is the dimension of the row space. Rank is the dimension of the row space. Okay, now this guy and this guy have the same row space. Okay, right? If you do, these are row equivalent to each other, they have the same row space. Okay, so what's the dimension of the row space? Oh look, right? All of these three rows are linearly independent. These rows with the pivots in them are linearly independent. right? And so we see that the row space is three-dimensional, right? In other words, that the rank is 3. Okay, the rank turns out to be the number of pivots, right? Because each of these rows with a pivot is independent of the other.
So the row space is basically the rows that are linearly independent. Or can you like just go over like what row space means?
Row space is just the span of these 3 vectors. Okay, you've got these 3 vectors, right? So, right, you have some vector, you have some matrix, right? Call it A. The row space of A is going to be just the span of the 3 rows: -1, 3, 4, 1, 2, -1, -2, -3, 8, 4, 2. Okay. It's just the span of these 3 guys in the 4-dimensional space.
Okay.
Okay. And in fact, we could have stuck with these guys as our basis, right? These guys are 3 vectors, and they span the whole space. They span the row space, so these actually are a basis as well. But the thing is that it wasn't so easy to look at them and say that they were linearly independent. Okay. So what we did was we did the Gauss reduction on it, and we said, oh look, the three rows are linearly independent, so these guys are a basis. Okay, so the space is 3-dimensional. Okay. Okay. Let's go on. So, okay. Is everybody okay so far? Right. So, if somebody gives, the point is this so far, right? If somebody gives you a matrix and says, "Give me a basis of the row space," then what you would do is you would do your Gauss-Jordan reduction on it, and then these rows, the non-zero rows, would be the basis of your row space. This is the same thing as the number of non-zero rows in your reduced row echelon form. Okay. So now we're going to make a connection with the null space. So take 1 minute and tell me, find the basis for the null space of this matrix A. Okay. So take, if you know what you're doing, it should take you 5 seconds. Okay? Turn to somebody nearby and say, here's how to do it, if you remember. We've done it before. I think you had it on your exam. Right, so the null space. What's gonna be my basis?
Like 10 sevens.
10 sevens.
2 sevens alpha.
2 sevens.
And then like a theta. Or like a 1. It would be like, well, there are 2 variables.
Okay, so you say, well, x1 equals 10 sevens x4,
Yeah.
x2 equals 2 sevens x4,
Yeah.
x3 equals
equals
0, right?
Okay.
And x4 is
X4.
x4,
Yeah.
right?
Yeah.
Right? Yeah. x3 is 0. Okay? And so you see that this is going to be multiples of this vector here. Right, multiples of 10 sevenths, of 10 to 0, 10, 0 sevenths. Okay. So this is this vector. This here is the basis of the null space of A. Okay. Right. This you've seen before, right? And you see that the dimension of the null space equals the number of free variables. Number of free variables, right? The number of free variables, right? 1. There's one free variable. All right. What is it?
So yeah, I don't understand how it's not good for variables.
X4 is your only free variable, right? Remember what the thing is that these guys are the lead variables. The one corresponding to the non-pivot row is the free variable, right? X1, 2, and 3 are the lead variables. X4 is the free variable. You see that the dimension of the null space is going to be just the number of free variables.
Okay, because it's the number of variables.
The number of pivots is 3, right? Right. You see that these you have a one-dimensional space here. Right. Everybody all right? Other than Mariah? Yeah.
Can you explain how do you get the null space?
How do we get the null space? Remember, right? You reduce down to here, right? And then you have that x1 equals negative, right? You come down to here and you say, well, right, x1 minus 10 sevenths x4 equals 0, right, x2 minus 2 sevenths x4 equals 0, x3 equals 0, x4 is just x1, right? And so x1 has to be, right, x1 has to be 10 sevenths x4, x2 has to be 2 sevenths x4, x3 has to be 0, and x4 is just x4. Right? And so you can factor out the x4, right? And you get 10 sevenths, 2 sevenths, 0, 1, right? Where x4 is anything. Right? And so you get the null space is just the span of this one vector. Right? Okay. Everybody okay? Okay, so what do you notice? What's the relation between the dimension of the row space and the dimension of the null space? What's the connection? Maybe I should not say the relation, but what's the connection between the dimension of the row space and the dimension of the null space?
So they add up to the dimension of
They add up to the number of variables, right? They add up to the number of variables, in other words, the number of columns, right? They add up to the number of columns, right? Because the dimension of the row space turns out to be the number of lead variables. The dimension of the row space is the number of lead variables. The dimension of the null space is the number of free variables. Well, the lead variables plus the free variables add up to all the variables, right? Well, then that's 4, right? So that is what is called the Bank Theorem. Okay, that's the Bank Theorem. That given any matrix, that the rank of A plus the nullity equals the number of columns. Okay. And the proof is just sort of like the general form of what we just did concretely, right? So you take your matrix and you do Gauss-Jordan reduction on it. Right? And then you just observe that the dimension of the row space is the number of free variables, the dimension of the null space is the number, is the number of lead variables, the dimension of the null space is the number of free variables. And those add up to n. Okay, so that's the main theorem. Let me have you do an exercise that will show you what's useful about this. Suppose you have an n by n matrix, and you know that the rank is n. And suppose you know that you've got two vectors, c and d, and you know that a times c equals a times d. Does that imply that C equals D? Right? Can you just cancel off the A? Can you just cancel off the A? That's basically what this is saying. Okay, so I want you to think about it for a minute or two and talk to each other. Of course, you use the Bank Theorem. Use the Bank Theorem. Okay, talk to each other if you have some idea, or even if you don't, it's okay.
You don't know whether it's A is not as good as
also like
Yeah,
the
like-
you can look all about zero, right?
Yeah, but if they're convertible, like the example. What do they just
Okay, okay. Anybody want to say something? Anybody have something to say? Does it imply that C equals D?
Yeah.
Yes. Why?
Because rank A equals the null space, the dimension of the null space is 0,
Mhm.
so the only solution. So like that means the only solution that A times the vector equals 0 could only be 0.
Mhm.
So that means A is invertible.
A is invertible.
Yeah.
Okay, that's so yes, if we have a square matrix. Yes, so absolutely right. So yeah, so you say, well, look, by the rank theorem, what happens to my pen? By the rank theorem, right? Since the rank of A is n, we know that the nullity is 0. Right? In other words, that the null space is just a 0 vector. Right? The null space is the 0 vector. That means that AX equals 0 has only the 0 solution. Right? Only the 0 solution. Right? And if this were a square matrix, then you'd say you're invertible, so you just you can multiply by inverse and just cancel out that A on both sides. Okay. Okay. If you don't have a square matrix, can anyone see that you can still do that? You can still cancel out. You can still get rid of the A. C will be equal to D. Anyone see how it happens, right? AC equals AD. AC equals AD. Eric.
I was just multiplying. AC minus AD equals 0.
AC minus AD equals 0. That means that A
Times C minus D.
C minus D equals 0. Right? Right? In other words, C minus D is a solution of this problem, so C minus D is 0. C minus D equals 0. Right? So you can't, so C equals D. Right? So yeah, C equals D, even though you don't have invertibility, as long as the rank is full, it's okay. You can
So if the rank equals n, could you also say that since if you reduce the matrix down, you'll get the identity matrix?
So
Because rank A equals n, so does that mean there's n number of pivots?
yeah, so you would end up with right. So you'd have the same number of columns would be the same as the number of pivots. Right? So every column would have a pivot. Right? So you'd have something like this with zeros beneath.
Oh.
Yes. And then?
Oh, no, so isn't that the identity matrix? But
It's not the identity matrix,
not,
but it's
because you
sort of
have
like the
zeros
identity
every
matrix.
time.
Yeah.
Okay, never mind.
Okay. Yeah, right.
Don't we have to know for this that the rank of the column space and the row space are the same? Because couldn't you have a matrix with a row of zeros at the bottom? If you had a 4x3 matrix and the rank was 3, you have a row of zeros. So then wouldn't that imply that C and D wouldn't need to be X? The row of zeros would just cancel out. If C and D had rows that were different, the zeros would just cancel them out.
So let me think for a second. The rank is n. That means that when you do the row reduction, then the number of pivots equals to the number of columns. Right? The number of pivots equals to the number of columns. That means that you can't have you can't have free variables.
Okay.
Right? You can't have free variables.
Okay.
Right? You're going to have only lead variables. Right? And they're all going to be, if you're trying to solve the homogeneous problem, then they're all going to be equal to 0.
Okay.
Right?
Yeah.
So no, right? You don't have any problem.
The lead variables would be 0?
If you're talking about the homogeneous problem. Right?
No, just in AC equals A.
But this is sort of the same thing. This is saying that A times C minus D equals 0.
Okay.
That means that C minus D has to be 0.
Okay.
Right? So yeah. So you're not going to have any free variables. You're not going to have any free variables. Okay. Okay. So does this make sense? Make sense to people? Right? This is one problem where you can use the rank theorem kind of in a cool way. So look, if the rank is full, right? If the rank is as big as possible, then AC being equal to AD implies that C equals to D. Okay. Let me ask an additional problem. What if you had this, right? That the rank was less than n, would AC being equal to AD force C to be equal to D? No, right? So people are shaking their heads already, right? All you would have, so if the rank is less than n, you would have that A times C minus D equals 0. So C minus D is in the null space, right? Right? For here the null space was 0, but here the null space could have stuff in it, right? So all that means is that C equals D plus something in the null space for some vector in the null space. Right? It means that they differ by some vector in the null space. Okay, right? Which is useful information. If you are taking a differential equations class, this fact has probably shown up, or will show up. Will show. Okay, will show. Okay, that is, you know, yeah. Okay, let's go on. Okay, so now let's get back to Mariah's question, which is, you know, do we not care about the dimension of the column space? So why don't we care about the dimension of the column space? Why don't we care about the dimension of the column space? And the point is the following theorem that says that they're the same thing. That the dimension of the column space and the dimension of the row space are the same number. Okay, so the proof starts off with the following simple fact that we learned on the first day. If A is row equivalent, well, this is not exactly the first day, but basically the first day. If A is row equivalent in U, then AX equals 0 and UX equals 0 have the same solution sets. Right? Elementary row operations don't change the solution set. Okay. Now, let me rephrase that. So what this is saying is that x1 times a1 plus x2 times a2 plus xn times an equals 0 if and only if x1 u1 plus x2 u2 plus xn un also equals 0. Also equals to 0. Right? In other words, if the vector x satisfies one system, it will satisfy the other system. Okay. But what this is saying is that, in other words, any linear dependence between the columns of A corresponds to a linear dependence between the columns of U. Right? So this is exactly the statement that we had on very early on in the course, but just phrased in terms of dependencies now. Let me give you a concrete example of this. So I'm going to sort of step out of the proof of the theorem, and then we'll get back to the theorem in a second. But I just to illustrate what I mean here. If we start off with the matrix 1, 2, 2, 3, 2, 5, 4, 8, -1, -3, -2, -5, 0, 2, 0, 4, and we reduce it. We end up with the matrix 1, 0, 2, -1, 0, 1, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0. Everybody, take a look. If I look at these columns here, I see that this third column is twice the first column. Right? Third column is twice the first column, and if I look at these columns, I see that this third column is twice the first column. Okay? If I look at this column here, right, it's -1 in the first column plus 2 in the second column. Right? This guy is a linear combination of these first two guys. -1 in the first guy plus 2 in the second guy. When I look at this guy, I see that if I take -1 in the first guy plus 2 in the second, -1 in the first guy plus 2 in the second, -1 in the first guy plus 2 in the second, -1 plus 2 in the second, I get this. Right? This fourth column is -1 in the first guy plus 4 in the last, 4 in the second, excuse me. 2 in the second. Okay? This is not a miracle, right? This wasn't just some accident or coincidence, right? This is what we said over here, right? Right here we're noticing that A1, 2A1 minus A2 is 0. I'm sorry, I should use U's because I call them. This is the 2U1 minus U3 is equal to 0, and same thing here. 2A1 minus A3 is 0. Right? Any dependence between the columns over here is a dependence between the columns over here. Right? And that's, it seems kind of crazy, but that's actually the simple observation we made at the beginning. That the solution set doesn't change when you do row reduction. Okay, so any dependence between the columns of A are going to hold when you go down to the reduced row echelon form. Okay, so now let's go back to the proof over here. Okay, we're trying to see that the dimension of the column space is the same as the rank of A. Okay, so let's get back to the proof. Say, well, look, let U be the reduced row echelon form of A. Notice that any column of U without pivots is a linear combination of those with pivots. And further, the columns with pivots are linearly independent. Okay, so let me come back to this picture here. what I'm saying in this last part here is that if I look at a column that doesn't have pivots, right, these columns have pivots. Let's look at the guys that don't have pivots. They're all linear combinations of these guys, right? This guy is twice that guy. This guy is -1 in the first plus twice the second, right? These guys are linear combinations of these guys, right? Any column without pivots is a linear combination of those guys with pivots, right? And further, the guys with pivots are linearly independent, right? These guys are linearly independent. Okay. In other words, right? These guys are a basis for the column space of U, right? In other words, the columns with pivots are a basis for the column space of U. Now, if we think about the column space of A, now let's go back to the column space of A. Well, we know that these guys are linear combinations of these guys, and these guys are linearly independent, right? So the corresponding columns, right? The corresponding columns of A are a basis for the column space of A. Right? Because these are linear independent and they span the other guys. Okay. So what does that tell you? That the dimension in particular, the dimension of the column space of A equals the number of pivots in U. Right? The dimension of the column space of A is going to be 2, right? The number of pivots. But we said earlier that the number of pivots is the same thing as the dimension of the row space, right? So the dimension of the row space and the dimension of the column space are the same. Okay. So this theorem gives you 2 nice facts. First, this business of the pivots, the dimension of the column space being the rank. And second, along the way, you get a way of finding the basis of your column space. It gives you a procedure for finding the basis of your column space. It says, do the row reduction, find the rows with pivots, and then the corresponding rows will be your basis. These guys will be the basis of your column space. Okay. Right. These guys, these 2 rows here, will be the basis of your column space. It does not say these guys will be the basis of A's column space. Right? So watch out. It doesn't say that. So, okay. So, along the way, you get that. Notice that the columns of A corresponding to pivot columns of U form a basis of the column space of A. Any questions? Any questions? Let me give you an exercise. I'm going to give you sort of a truncated version of the exercise. Okay, so we start off with a matrix 1, 3, 2, 2, 1, 4, 4, 7, 8. Okay, I'm going to do the work for you, do a little bit of work for you. This reduces to 1, 0, 2, 0, 1, 0, 0, 0, 0. Okay. I want you to take 1 minute and tell me bases, give me bases of the column space, row space, and null space. Okay. So it should take you, if you know what you're doing, it should take you 10 seconds. If you somehow magically understood everything, then it should take you 10 seconds. If it takes you more than 10 seconds, that's fine. Okay, let's do this together. Is there anyone that pops out at people immediately? Like, once I get to here, I do the row reduction, I get down to here. What can you tell me immediately? If I want a basis, I'm looking for bases, right? I start with this guy, I do the row reduction down to here. I end up with these 2 rows, right? That gives me basis of the column space. Okay, what's the basis of the column space? What's the basis of the column?
2.
Which columns?
1.
The first 2.
The first 2 columns of this one?
Okay.
This one?
And
The first 2 columns of A, right? So the columns, right? Since these 2 vectors are the basis of the column space of U, these 2 vectors would be the basis of the column space of A. Right? So 1, 2, 4, and 3, 1, 7 are basis of the column space of A. Right? Basis of the row space, it's there already, right? That's it, right? So 1, 0, 2, and 0, 1, 0 are basis of the row space of A. Right, because we don't change the row space. We do change the column space when we do row operations, but we do not change the row space. Okay, right? And then what about the null space? Can you just read it off? x1 has to be -2 x3, right? So -2 x3, x2 has to be 0, right? x3 is itself. Right. x3 is itself. So that's going to be the basis vector. Okay. Yes?
Can you explain why you changed the column space but not the row space?
So the row space, when you do the reduction, okay, these guys, these vectors still have the same span as this. Okay, these guys are linearly independent, so they are basis of this guy's row space, but this guy's row space is the same as this guy's row space. Okay, so these guys are basis for this guy's row space. Okay. When we do the row reduction, however, we drastically change the column space. Okay, look at the column space over here. The column space is the span of the columns. The span of the columns here doesn't even have it has 0 in the third variable. Right? Over here, there's nothing that says that the third variable has to be 0, right? The column space of this guy is not at all the same thing as the column space of this guy. However, we do have that great observation that the dependencies between the columns here are equivalent to correspond to dependencies between the columns here. So you say, oh look, these two guys are linearly independent, and this guy is dependent on the other two, right? This guy is in the span of these two guys, right? So that tells me that the column space of U has these two vectors as the basis. Okay, but that tells me that if I look back here, I see that, so over here I see that this guy, this last vector is twice the first one, right? So if I'm thinking about a basis, I throw that guy out, okay? Throw that guy out and keep only these two vectors, right? I come back here and I say, oh look, this last guy is actually twice the first guy. So, and I throw it out, and these two guys are a basis for this guy's column space. Okay, so I can't use these guys as the basis for this column space. They're completely different things, but the relations between the columns here correspond to relations between the columns here and vice versa. Okay, so I know that these guys are a basis. I know that these two guys are my basis for A's column space. Okay, that's it. Sorry to keep you over.